So I was just at this point where I was talking about the definition of, sorry, the a property which convex functions satisfy, which is f of y exceeds f of x plus gradient of f of x. Okay. So basically, what this says is simply that if you take the linear, you take the, so this is the gradient. Okay. If you take the gradient, if you take uh, the linear function which is created by the gradient, the linear form, okay, it forms an underestimator of the convex function throughout. Okay, this is true for convex functions. So this inequality is very, very useful in many proofs and many um, uh, proofs analysis of convex functions. Okay, this is for differentiable convex functions. More generally, a vector G in Rn is a subgradient of f at x, we'll call it g of x, if f of y exceeds f of x plus gx for every y. Okay, so this is generalizing this from differentiable functions to functions which may not be differentiable. So convex functions that we have seen need not be differentiable. So this simply defines a subgradient which is provides a linear underestimator for the function value. So for a convex function, what will happen is if you have a convex function of any type, okay. So for convex functions, f of y will be greater than f of x plus this subgradients for every x and y in Rn. Okay, so if you take a particular point, okay, so this point the function is differentiable. Okay, so you have a single clearly at this point it's a underestimator of the convex function. At points which are non-differentiable, like this one, you might have one or more subgradients. So, for example, this defines a subgradient. This defines a subgradient. This defines a subgradient. This defines a subgradient. Each of this will define a valid g of x vector at this point x. It will form a linear underestimator of the convex function. So, one terminology which is useful for you to know is, so this is always true for convex functions that the subgradients, if you form the linear, they'll form a linear underestimator, the linear form of y, okay, defined on x will be a linear underestimator on f of y. The set of all subgradients at a point at x is called the subdifferential. Okay, again, you might see this term somewhere. I just want to ensure it's at least you see it at least once. It's called the subdifferential of f at x. Okay, so you might have many points. So the simplest example that we saw is the absolute value function, which I where did I draw it? So if you go back to the absolute value function, so if you take so take this function, the absolute value function. This function is differentiable everywhere except 0. Okay. So if you look at delta f of the derivatives, so it's clearly 1 when x exceeds 0, -1 when x is lesser than 0. Between at 0, the subdifferential, there's no derivative defined, but subgradients are defined. It goes from -1 all the way up to 1. So it's an interval between -1 and 1. Okay, this is a subdifferential at x equal to 0. Okay. So for convex functions, the subgradients can play a role when you do optimization. Okay. Okay, so I wanted this to be introduced so that you see it once at least, this equation, because this inequality will show up quite a lot in convex analysis. Okay. Okay. Now before you end, I just want to mention one thing, which is for this class, uh, I was I the way you solve linear programs, there are many ways to do it. Okay. There are the way I'm going to, the way I would like you to try it at some point is you can try using this package called Jump. Okay, this is linked to Julia. Okay, you can also do things through Python. Okay, so if you want to do work through Python, you can easily connect. Okay, what you will need is when you solve these problems is, see, there'll be a solver. Okay, there'll be an LP solver. Okay, and there'll be also an IP solver. Okay, and there are many good LP solvers. The ones that I think, which I've worked with, for which you can get academic licenses, which are very good, is Gurobi. You can get an academic license, just go online and get it. You can do it for Cplex if you want. Okay, there's something called Mosaic. These are all high quality solvers which will solve for you. These will solve you both linear and integer programs. Okay. Mosaic will solve you linear programs and some conic programs. Okay. For all of these, academic licenses are available. Okay. So you'll have to download this onto your own computers. Then there is a modeling language. Okay. Typically, modeling language to write the formulations. Okay. And there are many ways you can do this. You can directly go from your Python or whatever framework you like. One way is to go through this Julia and Jump. Jump is a package which works with Julia. Julia is basically a linear algebra type package. It works well. You will, if you go to Jump, you will find details on this, and you will find tutorials, including simple linear programs, including the diet problem, which I've already discussed, and so on. Okay, you can just go download it and try it at your own time. Okay, play about with it. Ultimately, when you're going to solve linear programs in your any of your practical applications, you're going to have to solve it by computers. Okay, so you'll have to implement this. Okay, and there are it's a there are simple ways to do it. Okay, and we can look at it later, but there are codes which do this, and you can try it at your own time. Okay, if I'm not sure if you want me to go through some coding in the class, but generally when I was studying, I did this on my own time. Okay, so it's good for you to do it at your own time. You can, and you don't have to use this. If you want to work through Python, that's fine. You can go from Python and you can link it to Gurobi and so on. There are other ways to do it. Okay, there are packages and other things. These days, what is happening is one interesting area of research is, and one thing I've found when I've taught optimization, especially to undergrad students, is formulating optimization problems is not always easy. Okay, that is like you might to write the right constraints is not always straightforward. Okay, you might think it's straightforward in some cases it's not. For some people it's easy, some people it's harder to do this. So these modeling languages give you ways to write it in algebraic. They're typically what's called algebraic modeling languages, which means that you will write things in words. Okay, you'll write things like for all I in 1 to m sum. This is exactly how I write my Julia, my codes in this. Sum, aij times xij xj less than equal to bj, something like this. Okay. These days, I think that there's an interesting development, which is people are trying to use large language models, basically natural text, to try to formulate LPs directly. Okay. And then, of course, you don't want to solve, you have to go back to these solvers, because these solvers are, of course, they're very solid solvers. They have implemented algorithms which will always work. Okay. So now there's an interesting area of even analysis, research, trying to use natural text to formulate LPs. Okay. At this point, so for those of you, you can try, try going into your whatever your favorite LLMs are and try to directly input an optimization problem. But you should try to use algebraic modeling languages to write your LPs too. Okay, so I want you to do this at your own time. Okay, and if you're not sure how to do this, we can talk about it. Okay, but whatever favorite LP solver you have, work with. My experience in the last 5-6 years is this works very well with these things. Okay, it works very well. Okay, it's very easy to use and it works very well. Okay, but you might have your own favorite modeling language. Okay. Okay, we'll stop here. I'll see you on Wednesday. What we'll do next week is we will start with the geometry of linear programs. So we will talk about things like basic feasible solutions, polyhedron. We'll talk about extreme points. How do we visualize the feasible region of LPs, and how do we model it algebraically? So it'll be a lot on that next week. Week three, we will start with the simplex method. Okay, but next week I want to do geometry basically. Okay. Okay. If you've got questions, you can ask me. Otherwise, I'll see you next week. Have a good break. Have a good weekend.